just as a review, remember that flying drones is a delicate balancing act, right? We have to remember the four forces, right? We have thrust that pushes the drone forward, and thrust. Then we have drag that's resisting that. We have weight or gravity. And then we have to have lift. When all four of these things are equal, the drone hovers. If you want to move in a direction, whatever direction you're going into, you're going to have to apply more thrust. When you apply more thrust, there'll be a little more drag, but you just have to have an unequal amount of thrust to drag. If you want to slow down, then drag becomes greater. You don't control drag, but you take less thrust to slow down. Okay, if you want to go up, you have to produce more lift. And that's, of course, propeller speed. Propeller goes up. If you want to go down, you reduce the amount of lift, and weight is more than, the weight of gravity is more than the lift that you provide. Pretty simple. Performance. The performance section of the FAA Knowledge Exam for sUAS has some basic aerodynamic definitions. For example, one area they're going to examine you on is the term angle of attack. What does that mean? All kinds of wrong answers, but it's the angle between the wing chord line and the relative wind. It's not the pitch of the airplane or drone, either one. It's not the axis of the airplane. It's just simply the term angle of attack is defined as the angle between the wing chord line and the relative wind. For example, my crude picture of a wing, it is the chord line, which is that line that goes from the leading edge to the rear edge. Relative wind is simply the wind as it's blowing across the airfoil, right? Remember those diagrams where the wind goes around it, low pressure in the top, high pressure in the bottom, basically, right? It's this angle between here, it's extended line out from the wing chord line, and the wind. This is being the wind. See, I need another pen here. That's all that is, okay? So just remember that. Another way the question might be asked is the angle of attack at which the airfoil stalls will remain the same regardless of the weight of the aircraft. All angle of attack is the angle of the wind and the wing. It has nothing to do with the size of the airplane, with the weight of the airplane. Or if you move the center of gravity, either one. The center of gravity is a stability issue. It's just this angle between the wind and the chord line. You recall that there is numbers like 16 degrees. When it gets to be 16 degrees, in other words, the wind is coming at a really sharp angle like that, it no longer sticks to the wing. So somewhere around between 18 and 16 degrees, most airfoils will no longer, they will stall. They won't provide lift. Those are the two things you really need to know or remember about angle of attack. There's more, of course. The more would be load factor. Aerodynamic term about load factor. They'll ask you a number of questions about that. For example, which basic flight maneuver increases the load factor on a UAS as compared to straight and level? So they're asking the question, you're just flying straight, or hovering, or just flying straight. The load factor when you're going straight, when you're not going up or down, it should be 1 G. But when you're in a bank turn, now you're increasing the G's. That was all what that whole chart was in the supplement, where you calculate it all out. And they will get more specific on those charts. But the basic question is, which flight maneuver increases the load factor? Of course, B, turns. Another related question is, when operating an unmanned aircraft, the remote pilot in command should consider that the load factor on the wings or rotors may be increased anytime the aircraft, and the correct answer, of course, which is anytime the aircraft is subjected to a maneuver other than straight and level. So straight and level, that's like the key thing. Straight and level produces no increase in load factor. Turns, sharp climbs or descents produce some kind of a load factor. If you climb up to 400 feet and you do the emergency stop, the propeller blade stop, now the drone goes to 0 Gs momentarily as it drops, okay? That's not good because the props have stopped turning and you fall to the ground and it crashes. In a rocket launch, the person is subject to more than 1 G as you're accelerating upwards, or in a fighter aircraft. So that's another essential question about load factors. Another question about stall that I'd forgotten about, but a stall occurs when the smooth airflow over the unmanned aircraft's propeller is disrupted and the lift increases, the lift reduces rapidly. This is caused when the propeller exceeds its critical angle of attack. As we said before, whenever you exceed the critical angle of attack, you are going to stall. Critical angle of, and that's just the critical angle of attack between the relative wind and the wing, or airfoil is a better word, airfoil chord line. When that angle gets to a certain point, somewhere around 18 to 16, you'll be exceeding the critical angle of attack. And you're going to get a stall, or at least the airfoil over the top of the wing will start to get disrupted at some point. But that point is defined as the critical angle of attack. And then we have questions on the chart. Refer to figure 2. If the UAS weighs 30 or 10 pounds, what approximate weight would the UAS structure be required to support during a 60-degree bank turn to maintain altitude? Well, it's just a simple look at the chart, figure out just go to the chart, figure out where the bank angle is. You can use either side of the chart. You don't have to use both of them. It's a 60-degree bank. You go up there at 60 degrees. It says load factor 2.0. Well, you multiply the weight of the drone by 2. So in this question, if the drone weighs 10 pounds, the propeller blades have to support 20 pounds because it's 10 times 2. Simple. Those are pretty easy, basic questions. The test really is not that complicated, but of course, like I've said before, you need to slow down and read the question. Look for as much information you get before you answer the question, and later, if you're not real sure, go back and look at that question again, just to double check. Load factor question. An increase in load factor will cause the unmanned aircraft to stall at a higher airspeed. Now, don't get confused about this. Just saying, as you increase the load factor, you're going to increase the angle of the relative wind to the airfoil chord line. So we don't want to get too confused about that, but basically stall speed increases in proportion to the square root of the total load factor. Thus, if you had a load factor of 4, aircraft will stall at a speed which is double the normal stall speed. The question is actually the choices for this particular question. I'll read the question again. An increase in load factor will cause the unmanned aircraft to A, stall at a higher airspeed, that's the correct answer. B, tend to have a tendency to spin. No, that's not it. C, be more difficult to control. No, not necessarily. A is the best answer. It's going to be more difficult to control, I admit, but that's not the best answer. And of course, the FAA often asks questions that have 2 reasonable answers. One is better than the other. We have a question on the exam that is arguable. It reads like this: the most critical condition of launch performance are the result of some combination of high gross weight, altitude, temperature, and then it gives you 4 answers, possible answers. A, which is the answer they're looking for, is unfavorable wind. Because they've already mentioned high gross weight. Yeah, that's important. If you're very heavy, it's going to be hard to launch. They mentioned altitude. Yeah, if the air is thin, it's going to be hard to launch. They mentioned temperature. If it's hot, it's going to be hard to launch. But the choices aren't any one of those. They've already stated that in the name of the question. They're asking, is it unfavorable wind, or is it obstacles surrounding the launch site? Well, maybe. Is it your power plant system? No, what's that got to do with it? So now you have two choices. You've eliminated power plant because that's just the engine and the motors. That's not a problem. But you're looking at unfavorable wind or obstacles surrounding the launch site. Unfavorable wind is their choice for the correct answer. So that's the one. Believe it or not, you can argue all you want, but they're looking for unfavorable wind, just so you know. Another, I wouldn't call it a trick question, but it's a little obscure, but it asks this. The amount of excess load factor, we're talking about load factor again, that can be imposed on the wing of an airplane depends upon the speed of the aircraft. So the faster you go, abrupt movements of the control produce more load, more rapid load on the wings or the propeller blades for that matter. Drones automatically compensate, but I know the FAA asks a lot of questions about fixed wing aircraft. You don't get confused, because yes, right now we have quadcopters, but there will be a time when fixed wing drones are going to come into their own. Right now they're extremely expensive, but there will become a time in the future, if you're a professional drone pilot, that you're going to be flying a fixed wing drone, and you'll need to know this. But the FAA asks a lot of questions that seem to be not related to drones. It's just because our minds are a little bit narrow right now. Broaden your mind. Again, the amount of excess load that can be imposed on the wing of an airplane depends upon three choices: the position of the center of gravity, speed of the airplane, B, or abruptness at which the load is applied. Well, they're saying speed of the aircraft. And their arguments, by the way, are at slow speeds, maximum available lifting force of the wing is only slightly greater than the amount necessary to support the weight of the UAS. However, at high speeds, the capacity of the flight control or a strong gust of wind may increase the load factor beyond its safe limits. In other words, you could break the airplane. The faster you go, the more likely to break. Have you ever seen the $6 Million Man? You know, he's a test pilot. It is an old TV program, but still, he's flying this supersonic airplane and the wing falls off. What happened? He was going very fast. It's a test airplane, very fast, and a gust of wind hit or something like that, and it was too much load on the wing fell off and he crashes. And then when they get him to the hospital and they replace his legs with bionic legs, his eyes, got this eyeball that can see 500 miles, it can run at 80 miles an hour because he's got two bionic legs. His muscle, now his arms are super. You have to check out the TV program. In light of that same question, another question comes up. In a 45-degree banking turn, a small unmanned aircraft will, and the answer is stall at a higher airspeed. So, okay, don't mess this up. Angle of attack is different. Okay, an angle of attack is the angle at which the airflow is no longer smooth. That's critical angle of attack is where it will stall. Speed also has to do with it, as the faster you're going, the quicker you're going to come to this angle of attack. So, right? I mean, at a 45-degree bank turn, a small unmanned aircraft will stall at a higher airspeed because you're imposing already an angle of attack, an additional angle of attack, in order to support the weight of that turning motion. Another super basic question: what purpose does a rudder perform on a UAS aircraft? You don't have a rudder in your quadcopter, but still they're asking the question. They're just simply saying a rudder controls yaw. And, well, you're just going to have to accept that. Eventually, like I said, you may be in a fixed wing drone and have to deal with that, where it will have a rudder. Most likely it'll be automated, but still, the FAA has these questions that they're asking you to answer. A couple of other basic couple other basic questions. What would be the consequence of operating an unmanned aircraft above its maximum allowable weight? And the answer is simply shorter endurance, because it's going to require more energy to turn the props in order to support the heavier weight. We don't have maximum allowable weight figures for these drones, but still, they're like that. This is a professional course. You'll be expected perhaps to carry loads. You need to be aware of that. Let's see. Now the question is, according to 14 CFR Part 107, who is responsible for determining the performance of a small unmanned aircraft? Well, that goes back to that same old question that comes up. A remote pilot in command, or any pilot in command, is responsible for all aspects of the operation. Legal, as well as the safety concerns, as well as the performance of the aircraft. Whether all of those things that we've covered in this course. A couple of other questions on center of gravity, or, well, that was about weight and balance. Another couple of questions on balance comes basically like this. Unmanned aircraft loaded with the most rearward center of gravity is less stable at all speeds. The choices are less stable at all speeds, which is correct, more stable at slow speed, more stable at fast speed, nah. If the center of gravity isn't properly managed, it needs to be near the center of gravity, it's going to cause stability issues. That's the major issue. Yeah, remember, center of gravity is simply, again, my little picture of the drone, looking from the back end. You could look at it which way you want to, it doesn't matter to me. But we have lift here, we have gravity here, but the gravity is going to act off the center of gravity. So if you have a big old weight hanging off the wing here, this propeller blade is going to have to work really hard to balance this one here, or hardly turn at all. And so it's going to be less stable. It's going to create a greater need for power, whether it's electricity or nuclear powered or gasoline powered or helium, whatever. It's going to create a need for more electricity, so it's going to reduce performance, but it's also going to reduce the ability for the drone to turn that way, or no, to go this way, because it's not going to have enough lift. Well, no, go this way. When you want to turn that way, it's going to be hard because this is already running at maximum RPM just to hold the thing up, level flight, so it's not going to be as stable if you don't have the center of gravity in the proper place. And of course, another question was, they have another question. When range and economy of operation are the principal goals, in other words, you want to go a long ways, or you want to hover, you're doing surveillance and you're peering down at a particular parking lot to make sure, I don't know, make up your own scenario. If you want to be there a long time, you don't want to be flying around doing a lot of maneuvers. You want to just use long-range cruise performance. Just let the thing just idle, just at the minimum amount of power in order to keep it where it needs to be. But the question answer is specifically specific endurance, which we don't know what that means. Long-range cruise performance is the answer to the question. Total range is dependent on both the fuel available and its specific range. When the range and economy operations are the principal goal, the remote pilot must ensure that the UAS is operated at extended long-range cruise condition. Again, that's probably more related to, the numbers are more related to a fixed-wing drone, but we can take that principle in our mind and say that means we just don't need to be moving around a lot. Just stay in one place, not use a lot of maneuvering energy in order to stay up as long as possible. To ensure that the unmanned aircraft center of gravity limits are not exceeded, follow the loading instructions specified in the pilot's operating handbook or the UAS flight manual. Okay, right now, very few manufacturers are producing an operating handbook. They have little hints, little tiny pieces of paper that tell you a little bit how to run the thing, but these are mostly recreational drones. As you move on in your career, you're going to move into professional drones, and they're going to have these numbers. So you need to know. It's the pilot command's responsibility to ensure that the operation limits, as well as weight and balance limits, are not exceeded. And you'll find those in the pilot's operating handbook or a flight manual that comes with the drone. It'll have specific weights and speeds and all of the things you need to know about the drone. Study. Everything about being a professional means continued study. You're going to get new aircraft, exposed to new aircraft often, hopefully. Otherwise it'd be a pretty boring job. If you just have one drone, you fly that for the rest of your life. No, you'll have new equipment as time goes along, new developments. Well, you need to pull out the book and read up the information. Not to mention, of course, all of the regulation changes that are coming too. So it's an exciting career, but it requires zero effort. It requires constant learning. A couple more questions. What is the best source for UAS performance data and information? Manufacturer publications, their information. The other choices might be pilot reports or estimates based on similar systems, but that's the best answer is the best source for performance data and information is from the manufacturer of that particular unit. Another question, you're operating a UAS that does not have GPS or some kind of altimeter measuring equipment. How can you determine the altitude you're operating? Well, their answer is gain a visual perspective of what 400 feet looks like on the ground before in the flight. So you look down across the field, and you may want to pace it off with your, pace it off or measure something that you can see on the ground, and then sort of look up. That's their best answer. The not good answer for them, for the FAA, is operate a second UAS that has an altimeter to know how to do it, or their third bad answer is operate the UAS in proximity of a tower known to be 400 feet high. No, they're saying just gain a perspective, look up there. And again, the FAA is being gracious here. They're trying to not be authoritarian. They're giving you a break. They're saying, okay, look, if you're 420 feet. If you're in good faith, you did the best you could to figure out how high that is, okay. They're not going to jump all over you for being a little off. On the other hand, if you're doing it constantly and you don't really give a flip about measuring, they're trying to figure out how high you are, then that's probably going to be a problem eventually. Like I've said many times before, don't be annoying people by doing things. 400 feet and you're bothering somebody, that's just going to be a problem. Or if you scare a pilot of a manned aircraft, that's going to bother people. Those kind of things you're going to get in trouble for. Flying, misjudging 400 feet, don't obsess over that. If you have a drone, though, that tells you how high you are, don't go over 400 feet, because that stuff's recorded, and they can pull up the data and find out what you're doing. The new remote ID, remember, does give or make it available what your altitude is. By the way, the remote ID is not only, at this point, is available to the law enforcement, but also to anyone who buys the equipment that is curious enough to buy the equipment and receive those signals. So any public citizen could know how high you are, how close you are, how fast you're going, all of the things you might be doing in your drone. That was a major struggle during the process of formulating these laws. Is the drone user groups were saying this is just going to could cause some problems where some thief would track out where you are and steal your unit or rob you or something like that. Yeah. The FAA didn't go for that argument. They said, nope, we're going to make it available. Likewise, a question about a very similar question. You're operating a UAS that does not have GPS or an installed ground speed. How do you determine the speed you're operating? And their basic answer is dead reckoning. Dead reckoning is just a navigation term that just says you're seeing how long it takes to go between 2 points. So it's really not a helpful answer, but that's probably the best answer there is. The other ones are pilotage or wind triangle. None of those would really work very well with that. But without a GPS or some kind of a manufacturer's performance data, you determine the speed by timing the ground speed of the UAS when it's flown between 2 fixed points. So you measure off, well, it's like if you're on the interstate and they have, I don't know if they still have that, but they have mile markers You're driving along and you take a time. If it takes 1 minute to go 1 mile, you're going 60 miles an hour. But you're not going to fly a drone for a mile just to find out what speed you're going, but it's the same concept. A quarter mile would take 15 seconds. A half mile would take 30 seconds. And that would be 60 miles an hour, or get through that way. The answer that they want, though, is dead reckoning. Another question, how can a remote pilot determine the altitude of the terrain and structures where the flight will be conducted? Obviously on the sectional chart. That's why we studied that. And there'll be a bunch of questions on that as well in a separate section. But yeah, the sectional chart has the heights of the towers, right? A tower has a bold number, which is the mean sea level altitude, and then has brackets for a smaller, not bold letter, which tells above ground level, how high the tower is above ground level, which is what we care about as drone pilots.